This is 2014 study guide problem that they released before AP Physics 1 started. So the problem states a student hangs a 125 kilogram object on a string, sets into oscillation, and obtains the data for the position and velocity of the object as a function of time shown in the graphs below. Let's look what the questions ask. On the grid below, sketch the potential energy of the object, spring Earth system, as a function of time. Explicitly label, always when they give you the graphs, make sure that you label any intercepts, asymptotes, maxima, or minima with numerical values as appropriate. So let's look at the graph, the first one, the position that is given, because we need 1/2 kx squared, correct? If it is in equilibrium, so this is how far, this is the half of it is going to be the amplitude. So if it goes between 0.5 meters to 1 meter, then the amplitude of the oscillation is 0.25 meters. We do not know where the original position of the object was as they attached the mass, so we do not know what k is equal to find the potential energy. But we can look at the graph and find the kinetic energy, and maximum kinetic energy of the graph is equal to the potential energy of the graph original. So I can figure out the kinetic energy of the graph is equal to 1/2 of the mass, 1/2. The mass of the object is 0.125, and the maximum velocity shows as 1.5. There will be always, with measurements, you will always have some discrepancies with the graph. So you just ignore those little bumps here and there. So the actual graph is going to look something like this. You ignore those bumps. So it looks like maximum velocity is 1.5 meters per second. So that's 1.5 squared. So the kinetic energy of the object is equal to 0.14 joules. So this is maximum kinetic energy. This maximum energy comes from potential energy of the spring. So 1/2 kx squared is equal to 0.14. So your x is your amplitude, the maximum displacement. So from here you can find what k is equal to, and we're going to use this data in a second. And I have 4.48. And that is measured newtons per meter. So this information is given, I can use now, and potential and kinetic energy is given maximum too. So that means that was maximum potential energy. So let's look at the graphs and see how that will go together. So I rewrote for you everything that we found so far. We know the mass of the object, we know the amplitude of the object, we know, so I have the amplitude of the object, kinetic and potential energy of the object, and the spring constant. And I'm gonna mark the graphs where my kinetic energy is going to be maximum. It's going to be at these points. So my kinetic energy is maximum at 0.25. So my kinetic energy is maximum. I'm going to do maximum right here at 0.25, and I have to mark. So every time I do the graphs, I have to mark what my values are. So right here, I'm going to mark this point as 0.14 joules. So that is my maximum value for energy. So I have maximum kinetic energy at 0.14, right? I have it at 0.25 seconds. I have it 0.75 seconds. I have it at 125 seconds. And I have it at 175 seconds. And at 225 seconds. Somewhere here. And then I have 0 kinetic energy at these points where it intercepts the x-axis. So I have 0, I have 0, I have another 0, I have another 0, and I have another 0. So it looks like my kinetic energy is gonna look like this. So this is the kinetic energy graph. And you cannot have a negative kinetic energy. I should fix this a little bit. Okay, so that would be my kinetic energy graph. For potential energy, wherever you have maximum kinetic energy, you have minimum or 0 potential energy. So they just have to flip. So I know if I had the point here, now I have the point here. Where I had kinetic maximum, I have potential minimum. So this is where my potential energy is going to be equal to 0. Now I have to figure out where my potential energy is going to start. And I see that when I had 0 kinetic energy, I will have maximum potential energy. So, and then goes to 0. When I have 0 kinetic energy, I have maximum potential energy. When I have maximum kinetic energy, I have 0 potential energy. And again, 0 kinetic energy means maximum potential energy, and it repeats. So my purple graph is going to be the potential energy graph. And again, your maximum is still 0.14. So I'm going to go back to this graph right here. And it looks like if this is your x-axis, and oh wait, this is not, they tell you, oh no, it is, okay. And this is, so there is an error right here, yes. They just wrote the graph numbers all the way at the bottom. And it looks like I'm gonna have my potential energy maximum. Let me write what my numbers mean. So if I say this is 0.1 and this is 0.2, then my maximum energy is gonna be starting from somewhere here, and it has to go in between and back to 0.5 up. So it's gonna be something like this. And so I'm just redrawing the graph that I did for the other graph on my graph. So I have maximum at 0.5, I have maximum at 0.5, I have maximum at 0, I have maximum at 0, and I have maximum at 1. So I have maximum at 1, maximum at 1.5, maximum at 2. So I'm just checking that my graph was right. So that would be my potential energy graph. So here I would write that this is my potential energy. I have to do my abbreviations. Here's my potential energy, and measured in joules. And this is my time measured in seconds. For B part, they ask you on the axis below, sketch the acceleration of the object as function of time. Explicitly label any intercepts, asymptotes, maxima, or minima with numerical values as appropriate. And I'm going to go back to this graph just to see what the graph is going to look like, and then I'm going to do my maximum calculations of the accelerations to see what it's going to look like. So your maximum acceleration is going to be happening If you remember, let me do it right here for you. If you remember this circle, the videos that I posted for you in lessons, if your eye is right here and observing a circular motion from the side, so this is front view, but you're looking on the side, and you see a dot right here that is moving, you will have zero velocity at this moment because you don't see the length of this velocity. You will have maximum negative velocity at this point. You will have zero velocity at this point, and you will have maximum positive velocity at this point. So this would be for the velocity graph. For acceleration, acceleration is always pointed toward the center, centripetal acceleration. So your maximum negative velocity is at this point. Your maximum or your zero velocity acceleration at this point, your maximum positive acceleration at this point, and you have zero acceleration at this point. And if this does not make sense and it's confusing, go review the lessons one more time so you understand the video that I posted for you. I believe it's 1969, 1961, the video, the old video that was there, about 30 minutes. If there was a bob and the bob was moving there and back, it would have zero velocity here, and you will see it from the graph, so you will not see a line. If you look in sideways, you will not see this, like the length of the line, you will just see a dot. So zero velocity here, zero velocity here. You have maximum negative velocity on this side, you have maximum positive velocity on this side. So it's the same as looking at this graph. You have a zero velocity, maximum positive, zero velocity, maximum negative. So when you have after you have, let me go back right here. After you have maximum negative velocity, you have positive acceleration. So after you have maximum negative velocity, I'm going to switch to red color. After maximum negative velocity, you have positive acceleration, maximum. So the slope of the graph right here at 1 second is going to be maximum acceleration. The slope over here is the acceleration, and it is zero. The slope over here is zero. So you have zero acceleration, maximum acceleration, positive, zero acceleration, maximum acceleration, negative, zero acceleration, again, maximum acceleration, positive, zero acceleration, maximum acceleration, negative. So if I want to redraw the graph, let me erase this here. If I want to redraw my graph for acceleration, then it would look like this. At this point, so in the red is going to be acceleration. At this point, I have maximum positive, then I have zero, then I have maximum negative, then I have zero. So the slope of this graph is zero, so I have zero acceleration. The slope of this graph right here is maximum positive, so I have maximum positive, and it will keep going there and back. So at this point is gonna be zero maximum negative, zero maximum positive, zero maximum negative. So now if I redraw my graph, I should have maximum negative at 0.5, 0.125, and 0.25, and maximum positive at 1 and 2 and 0. So going back to the graph, right here, here's acceleration. So I have graph looking like this. Right? 5, 1.5, and 2.5. Yes. So this would be my graph for acceleration. Now I have to figure out the values. So what is this value, and this is what is that value of my acceleration. So this is acceleration, meters per second squared over time, which is seconds. To find acceleration, so when the bob is, or the mass is being pulled this way, so let's say this is equilibrium, and it goes there and back. So it can go in this position, it could be in the other position, and this is your maximum amplitude. So the forces acting on the object here would be on the bottom would be kx the force of the spring, and mg, and there will be acceleration at this point, and I'm going to calculate that acceleration. So what I have is kx minus mg equals to ma. So k is 4.8 and x is 0.25. So let me erase this one. So I have 4.48, x is 0.25, mass is 0.125 times 10, and all of it is equal to 0.125 times acceleration. So acceleration is equal to, I get negative 1.04 meters per second squared. So I got my acceleration. So the maximum value is going to be 104, positive or negative? Negative 104 meters per second squared. Next, the student is given a rubber band and asked to determine whether the relationship between the restoring force exerted by the rubber band and the amount it is stretched is the same as that of an ideal spring. So for that reason, I have to, so I know the force of the spring is equal to kx, with a negative means it's always the opposite. So the force acting on the spring is proportional, or on the mass by the spring is proportional to its stretch x, or the amplitude by which it's being pulled down, and k is the constant for that specific spring when you buy it, so that is a constant. And so if you would to graph a graph force over the amount of by how much it stretches, you would get a linear relationship. So there would be a really linear relationship, and I'm gonna ignore a negative sign for now because it's just the sign that tells you that force is always acting in the opposite directions to what you're doing to the spring. So you would have a linear relationship where your slope of the graph is actually the spring constant, because if you look at this graph, y is equal to mx, y is your f, x is your x in this case, and m is the slope. So there would be a linear relationship. So the question that in C asked is, describe an experimental procedure that the student could use to collect the necessary data, including all the equipment that the student would need. So what would I need? So if you are given a rubber band, then you need to attach the rubber band to something. So I will need for that rubber band something to hang on. So I need some kind of a stand. Then I would have to attach some mass to rubber band, and that rubber band is gonna stretch some distance x. So with data I will need to do, and probably for a few different cases, so I'm gonna have different masses, m1, m2, m3, and I'm gonna measure the x by how much it's stretched every single time. So for M1, there's going to be some number, M2 some number, M3 some number. So I'm going to record those numbers, and after I record those numbers, I will try to graph it, because I know what the M is equal to. I know what my mg is equal to, so I can calculate my mg for every single one of them. So that's going to be your force acting on the spring when it is in equilibrium, or on the rubber band, and then by how much it stretches. And if your graph comes out as a straight line, then you could say that the rubber band has the same effect, or all the formulas that you could use for a spring you could use for the rubber band, because it behaves the same as if it was the spring. So for D part, they ask you, how should the student analyze the data to determine whether the relationship between the restoring force exerted by the rubber band and the amount of the stretch is the same as that one in ideal spring? What evidence from the analysis would you use to make the determination? And your D answer would be this answer. So that's what you're looking for. So if your data collected gives you this result, then you can say that the relationship between the rubber band and the spring is the same and follows the same formula. I will post the link to the explanation of this problem online. I didn't solve it exactly the same as AP exam would solve it. The answers are the same, the explanation is a little bit different. I want you to look at their explanation and their problem written online as well. So it's good to see the student responses compared to how you would respond and how they would grade this problem. Always when you take the AP exam, they say here at the top that it's a 12-point problem and suggest that the time is 25 minutes. So after you answer your question, I answer my question like if I would answer my question. And then after every problem I solve, I usually go back and I say, okay, this problem is 12 points. I know where my points would fall in. Like let's say in A, I would give so many points. In B, I would give so many points. In C, I would give so many points. And then if I decided my A is going to be 3 points or 4 points, then I'm going to say, what would I give those 3 points for? And then when I look at my A, I'm going to say, okay, for A, I would give 3 points for labeling the graph, for doing the correct graph, for so for everything that you say you would give points for, you have to have an answer for every single A, B, and C section. And after you're done, it's this way the closest you will get to the way the grader is going to be looking at your problem. And also try not to write too much, because when you write too much, it's difficult to read. It takes longer time to grade, and they're already tired. They have a lot of work to do, and they check a lot of tests. So you want to be specific about only important information and not too much information.